Hello, everybody. Thanks for joining us for another session of EI Live K-12 for students and educators. My name is Cassie, and I oversee education and outreach activities at the Earth Institute. For those of you who aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind climate change and sustainability, and what we as global citizens can do. Experts that make up the Earth Institute are actually quite interdisciplinary. They include economists, business and policy experts, specialists in public health and law, and of course, earth and environmental scientists. The Institute is actually made up of more than 24 or so research centers and several hundred individuals who collaborate across many different departments at Columbia University. So what we're really hoping to do with these sessions is to bring that science to you through our experts. And we have these weekly sessions. Thank you for those of you who are returning, and welcome to the folks who are joining us for the first time. We've got these weekly sessions until the end of June on a variety of topics. If you'd like any additional information about the upcoming sessions, feel free to reach out to me directly. You have my email. And today, we're actually extremely lucky to have Frank Nitsche from Lamont-Doherty Earth Observatory. He's going to be speaking to us about what's happening with between ice and ocean interactions in Antarctica. And he'll also talk a little bit about his experience in Antarctica, as he's been there numerous times. Frank works at the Lamont-Doherty Earth Observatory, and Lamont is the largest piece of the Earth Institute. The fundamental science and basic science research that goes on within the Earth Institute is all based at Lamont. So a very important research entity that's part of the Earth Institute at Columbia. So Frank is going to do his presentation, and we'll have a couple minutes at the end, hopefully more, for Q&A. If you do have questions that come up during the session, please use the Q&A box. The chat is disabled. And we're also going to have a colleague from NASA GIST join us, so that she can share some NASA GIST. GIST as the Goddard Institute of Space Studies, and she's going to share a couple of resources from NASA with us. So Frank, whenever you're ready, take it away.
Thank you, Casey, very much, and good afternoon, everybody. Thanks for tuning in. So my name is Frank Nitsche. As Casey said, I'm a research scientist at Lamont-Doherty, and because in geophysics, I mostly study like the sea floor, but I've been on several Antarctic expeditions where we also look at the water column to find out like how like warm water would. I explain a little bit later. It's one of the main drivers for basically the melting of the Antarctic ice. I do also some work on in local areas. I work in the Hudson River and Long Island Sound, but today I'm going to focus on some basics of Antarctica. I mean, sometimes I guess if you hear about global warming and sea level rise, Antarctica comes up, and it's there's a lot of things that have been mentioned in some of the news articles. I want to give you a little bit of a background, what's going on, and why we think it's melting, and where and how, and a little bit of background on the Antarctic Ice Sheet as well. So let me hit there. Okay, so just, why do we care about it? Antarctic, we've noticed over the last century, basically, that sea level is constantly rising, and that's a global sea level curve here, and over the last 20, 30 years, that's basically increased. And the general idea is that it's to do with, the Earth is warming up, global warming. And a lot of, see here on the right, you see some graphs, some estimates from what are the different components that people think make up this sea level rise. So a lot of it is basically what is called ocean thermal expansion. That's the ocean just heating up by warming up, it's expanding. So this called a sea level rise. Then some of other ice caps and glaciers are melting. And then there's this part up here, which is Greenland and Antarctica. So these two don't make too much of a component at the moment of a global sea level rise, but their components still increasing steadily over the last like decade, and because there's still a lot of ice in Greenland and especially in Antarctica, I think the idea is that, you know, if we're seeing some major increases in sea level rise, it's going to come from these areas. So today we're going to be mostly talking about the Antarctic ice sheet. Just as a view, so Antarctica was on the southern hemisphere and on the South Pole, which is located here where the curve is. And it's basically divided in two components. So it's the East Antarctic ice sheet and then the smaller West Antarctic ice sheet. And to give you some idea how big Antarctica is, I have a rough estimate, a rough comparison to the US, the continental US. So Antarctica is much, you know, it's maybe the same width, but much higher. So it's basically bigger than the continental US, but that's not bigger. And a lot of it is made out of ice, which is very thick. So if you do a cross section from west to east through Antarctica, you will see that here's the East Antarctic ice sheet, which is mostly located above sea level. It's that's in kilometers, it's 3 to 4 kilometers, so that's like 2-3 miles thick. So that's a lot of ice sitting there. And if East Antarctica would melt, it would raise sea level by almost 60 meters. That's like 170 feet. So that's a lot of sea level that's sitting here frozen in Antarctica. And on the West Antarctic, it's smaller and in extent, and then the thickness is still like 1 to 2 miles thick, like 2 to 3 kilometers, and it would maybe be 3 to 5 meters, maybe like 12, 15 feet of sea level rise. But as you can see in this cross section, and I show you another map in a minute, you see that a lot of the West Antarctic ice sheet is actually below sea level, which brings it in contact with the ocean, and that's a major factor in melting, or where we see melting today. So if we go back to the Antarctic ice sheet, so that's just the ice on top, but if you imagine we can take all the ice away, what you see then is that's what Antarctica is looking without the ice, basically underneath today. So everything in bluish colors is basically below sea level. So you see that a lot of here in West Antarctica is actually pretty deep. It's over like a mile deep below sea level. Here we're like a large part of East Antarctica are actually above sea level. So they're not necessarily so easily in contact with the ocean, where the ocean, you know, really is in contact with the ice in West Antarctica. So how does basically an ice sheet or also a glacier works in general? So I think the main component of it that, you know, it's made out of ice, and this ice is formed by snow. So you have to get like, you know, water that evaporates, forms clouds, and when it gets into cold areas, it will fall down as snow, and the snow accumulates and falls like, you know, a mound, and over time the snow will turn to ice, and because it's building up higher and higher, its own weight of the ice sheet will cause the ice to flow very slowly from the center to the outside. So the ice is basically in motion, and in the center it will only maybe move a couple feet per year, so really, really slow. And in the outer skirts, it can speed up, and sometimes it will be maybe a couple miles a year. Not really fast, but you know, in terms of ice growth, this is really a large speed. And what you see is as it flows out, and the weight, it gets thinner and thinner towards the edges, and when it reaches the ocean, then it, you know, at some point it gets so thin that it starts to swim, to float basically, and then we create an ice shelf. And then at the end here, it's melting or breaking off, and then the icebergs are melting, turning to water, which then evaporates and creates more snow. And in some areas like Greenland, the ice is actually terminating on land, not on the ocean. So then it basically gets to a point where it's maybe warm enough that it can melt and then just run off. But in Antarctica, most of the ice sheet is terminating or ending in or near the ocean. And just to another graph here to show this in a little more detail what's happening at the edge when the ice enters the ocean. So again, we have the snow up here. Over here, then the ice is flowing towards the ocean, and as it's just moving there, it's actually getting thinner. And at some point, it's the whole ice sheet becomes so thin that it actually starts to float off. And the point where it happens is called the grounding line. And then the floating part of the glacial ice sheet is called the ice shelf. And when pieces of the ice shelf, it continues to float, and then there's some cracks forming, and then they break off. So this is actually how icebergs are formed. And well, that's the main mechanism for like how the Antarctic ice sheet or all the big ice sheets are operating. To give you an idea how it looks like, so this is a picture that I took from the Pineal Glacier ice shelf. So you can see people here from the boat, but to give you an impression like how thick this is, so this is actually what we've seen here. That's an ice shelf. That's already the floating part of the ice shelf, but it's like 40 to 50 meters, 120 to 160 feet high. And as you might have learned, so because ice is floating, only like 1/10 is above the sea and 9/10 is below. So even though this is already really tall, we have a 90%, so another 900 feet basically are below sea level. So this ice shelf, even though it's floating in the water, it's still very thick piece of ice. And so what's happening with the ice shelf is then it's breaking off. So this is, again, it's a Pine Island. It's basically the same glacier I showed in the picture, but this is a time lapse from satellite images. And the one thing you can notice, you can actually see here, that's basically a year worth of data, that how the ice is flowing along. So it's actually really, you can see really how it's moving, but only in this time-lapse movie. And then eventually the top breaks off, and this is a large icebergs that every couple of years they break off from this glacier, and they're really big, so like maybe like 5 to 10 kilometers thick, and then maybe like 40, 50 kilometers wide. So, larger than Manhattan Island, or break off maybe sometimes even half of Long Island. So it's really a big chunk of ice, and very normal procedure. All the ice shelves break off in pieces, once enough of the ice is moving along. And just because a nice picture. So once the iceberg's floating, the waves and winds and moves them around and shape them up, and you get some very interesting forms. Maybe this little arches in here, and sometimes when part of the base underneath, it's long 90% is melting off, then if some of this is melting off, it basically tips over to the side. You can see this is partly tipped over. So there's all kinds of shapes and icebergs you can see in the ocean if you go around Antarctica. So what's happening also then is that's another idea. So if we're thinking about like how does it affect sea level and not, so we have basically what's going on, we have snow falling, we call it accumulation on the ice shelf. And then we have, on the ocean side, we have basically icebergs breaking off, and also melting of the ice from underneath. So this is kind of the way how the ice sheet or the glaciers lose ice. And this gets then, through the melting, basically gets, the ice goes back in the ocean. And as long as there's, lose enough, the same amount of ice here, then we get an accumulation. The whole thing is in equilibrium, is basically stable. But if increase in melting here, then, for example, then we get, or if we break up more icebergs, then basically the whole thing starts flowing more quickly, and then we're losing more ice on this end than we can accumulate with snowfall. So if we lose more ice and snow falling, then basically the ice sheet is shrinking and sea level is rising. And it's the opposite can happen as well. So if we get much more snow accumulating on the ice, then we're losing on the floating part, then basically the ice sheet would grow. And this has happened during ice ages, glaciations, basically. But over the last couple of years, we basically have been losing ice. So whatever we're losing here is being bigger, larger than what's been accumulating. And how do we know that? So we've been monitoring, or like other scientists, especially from NASA, have been monitoring ice sheets with different satellites for different years, sometimes also from airplanes, where they use like the laser, that would be the green beams here. They bounce laser from the satellite to the ice sheet and measure the distance, so it can see how thick the ice is, or they're using radar waves as well. So if they can monitor the top of the ice sheet, how thick it is, and then basically determine over time if an ice sheet is losing mass, is getting thicker or thinner. And I have a little animation you can see. So one thing is, that's over like the last 20 years. So one thing you see is it's every year the sea ice outside is forming and melting. So this is kind of the pulse, what you see. But when you look inside, you see all the orange and red spots. This is where the ice sheet is losing mass, where it's shrinking. And then there's a few points where we get more snow than it's moving away. So there's a few spots where actually the ice sheet is getting thicker, but overall it's been thinning a lot. And you can see, especially in this area where we have the Pineal Glacier or the Thwaites Glacier, this is called the Amundsen Sea, there's been a lot of thinning going on. I have another map here that shows this status in a static map that shows us again that here, that's elevation changes. There's been really a couple meters of thinning happening in this area and some other areas as well, but mostly in this area here. And this map is also plotted the water temperature around Antarctica. And you can see that here we have more reddish colors, which it's water above the melt temperatures. There's like warmer waters here where it's like reddish, and then we have some areas where it's white or bluish colors, which are like colder waters. So there's an area where you have warm water reaching very close to the ice, to the shelf. And the idea is that this warm water is basically the driver that is melting the ice sheet in these areas. So this is another sketch of how we think what's happening. So we have this this warm water pool, which is called circumpolar deep water. This is relatively warm, and because in the ocean it's also pretty salty water. So if I say relatively warm water, it's like 2 to 3 degrees Celsius. So that's maybe 34, 35 degrees Fahrenheit. So it's not really warm water. You don't really, except if you want to do like a polar bear dip or something, you don't really want to go swim in this water, but it's it's definitely above freezing. So it's, relatively warm compared to the ice, where the rest of the ocean water near the glaciers is usually cooler. So some of this warm water will get onto the shelf, and because we have a thick ice sheet sitting there in Antarctica. It's depressing the continent a little, so we have a little dip, a gradient from the what's called the outer continental shelf to the inner shelf, and this denser warm water, once it makes it over this shelf break, the outer shelf, it will then basically follow the gradient down until it reaches the ice, and then it will melt the ice sheet underneath. And when it's melting, you get some melt water. This is fresh water will be mixing, and it will be a little colder, and then it's a little lighter because it's less salty, and then it will rise up and flow out. So we get the circulation of warm water coming in, melting and rising up. And if it continues, it will melt the ice in different steps. And to really better understand what's going on, we actually have to go there by ship. You can't really measure this easy from satellites anymore. So that's a part of my work. We're going to this area, finding out where's warm water, and like what are the pathways for the warm water to get to the ice. I've been on many expeditions over the years with different ships. So Swedish, it's this American icebreaker, German icebreaker, and most of this concentrated in this area where we want to study really what's going on with these glaciers, why they're melting so fast. There's another image of the ship, the Nathaniel Palmer, that's a US research icebreaker. And again, so it looks maybe a little small on this picture, but remember, this is very thick ice. So the icebreaker is basically 300 feet long and maybe 5 stories tall. So it's really a big ship, which you really need because you go there for 2 months and you have to go through ice, and have a lot of science equipment on it as well. But it's really nice. Things will go very amazing. So what we're going to do when we reach the area, so we're doing what we call oceanographic measurements. We're taking CDD, which stands for conductivity, temperature, depth. So conductivity gives you salinity. So basically, we measure salinity and temperature with depths to identify if there's like warm water at the bottom, if it's this salty water that we think comes from the further ocean, and better understand like the melt processes. So we have the actual sensor. It's actually inside of this device, hidden by all this plastic bottles. So there's the actual sensors in here, and then the bottles around it, they're there for taking water samples. So we can get extra water samples from the different water masses that we then can analyze in the lab on the ship or at home later. And when we do this, so we can get this curve that's here. In this case, it's temperature, basically. And we do see, especially for the red curve and some of the green curves, that, okay, so a lot of the water on the top is minus 1.5 degrees Celsius, or like 30 degrees Fahrenheit. So that would be much below freezing, but because it's still like ocean water, it has salt in it, so it doesn't really freeze so easily with this temperature. So it's just below freezing. It's the same effect that that's why people put salt on the roads and the sidewalks in the winter to freeze the ice. It lowers the melting point of the water of the ice if you put salt in it. So because it's salt water, so a lot of the surface water is actually like around like -1, or a bit deeper, it's maybe -1.5 centigrade. But then at the bottom, we see this big jump to warmer water, relatively warm. So it's like up to like 1 degree Celsius, or like 34 degrees, 34 degrees Fahrenheit. So it's not super warm, but it's above freezing, and there's a lot of water there. So that's enough to really start melting the ice that comes in contact with this water. So we use this to measure, basically the pathway of the water from the shelf to the ice. But because we cannot really go under the ice itself with the ship, it's, as I said, it's like 900 feet of an ice shelf. We you can use, or some colleagues have been using these robots, basically it's called underwater autonomous vehicle. So basically self-driving mini submarines that can measure or salinity and temperature and a couple other things as well. And so there's a big one here can go out for missions for maybe 2 days a piece and collecting data under the ice. And then sometimes the scientists put also these gliders or other floats out that can stay out for a couple of weeks or even months and take measurements. And then they have antennas on sending this data back. Also, these cannot really go under the ice, but this one can, which is really good. And to show you how this looks, so this is a Pineal Glacier. It's the same glacier where we saw earlier there's a breakup happening. And each of these lines, that's just like a map view, shows like a track of this robot and this underwater vehicle collecting data. And it's the summary of the data you can see on the right. So again, you see the ice shelf here. So we see like above zero, above sea level, like this, 40, 50 meters, 100 something, 120 feet sticking out when we see like how thick the ice shelf is underwater really. And then the robot went in, and it's not only going in, but it went up and down. So we get nice transect of the water temperature and salinity. And you can see here in red is the water, that's the warm water that's really above freezing. And one of the interesting finds was also that a lot of this really warm water doesn't actually make it quite to the ice in this case. There's only like some of it that gets over this. The black curve here is the bottom of the seafloor under the ice. And there was this huge bump in the way, this ridge that kind of blocked off some of the water, or most of the water. And some of it actually made it over. So it's in yellow, so it's not quite as warm as the red part here, but still warm enough to melt the ice. And you can see some of what I showed earlier. So it gets here, the warm water, and then when it mixes, it gets colder again. And then, it moves back. So we see, we can see the picture of what's happening to the warm water underneath, but we also get to identify these kind of obstacles that really maybe prevent some of the warm water to get to the ice shelf. And sometimes, so we go there with a ship, usually in the Antarctic summer, which is our winter, but then we have to leave before the big ice comes. And some other colleagues started then engaging some of the native community to help us with our research. So they've been, there's a lot of seals. So this is an elephant seal, female, and so they've been attaching this a mini version of the CTD device on the head. So they glue it basically on the fur. That's like, a bit like getting something sticking on your hair. And they stay on for like 6 months to a year if they're lucky. And then each year when they're molting again, then they're losing the fur, they're renewing the fur, just drops off. So it doesn't hurt them, it doesn't disturb them further. But they go a lot of places where we cannot go with a ship. We get a lot of data. So this is some data set showing that where they are all over the place, and they dive deep. They dive very low. So some of these elephant seals can go like over a mile down, not a mile, like 500, 600 meters, so half a mile basically down. So dive a lot, so you get a lot of water profiles from them as well. So we're putting all this data together to understand what's really going on. And so the idea is really what I showed earlier, that we get this warm water called circumpolar deep water that's out here that's getting driven in some places of Antarctica especially in the Amundsen Sea. It gets onto the shelf and then reaches the ice where it's melting the ice from underneath. And when it's melting the ice underneath here, it's kind of thinning the ice shelf and the earlier ice here, and then more and more ice, because it's the front here becomes steeper. So basically then it's more ice and it's flowing towards the ice shelf, also from inland, and it's flowing faster. So more and more ice is coming to the front and then gets melted, and then basically it's the glacier, the ice sheet here, or the glaciers are losing mass and contributing to sea level. And then there is a concern that at some point, there's more warm water getting over these ridges and bumps that we find, and then we'll basically having more melt in the future. If this, if we're getting more warm water out here and it's getting warmer and warmer over time, it might eventually get more warm water over these bumps and then more of the ice sheets. And then, we're getting this much stronger component of Antarctica to sea level rise, and that will increase sea level over the world. So there's information that we're producing just to clear up. This will then be used. So people who do model and try to predict what happens to ice sheets in the future, they're using this information to run the models. So this is an example that was just recently come out in Science, like I think last week. So has been in the news in the last week as well. So they're using like a scenario where we don't manage to stop global warming by 1.5 degrees or 2 degrees. They're using here, for example, +3 degrees warming over the next, not only to the end of this century, but over the next 300 years. And you can see that maybe over the next 80 years, there was some ice lost here in this area. We see some thinning, is not too clear, but there's some contribution, which we're still not exactly sure. This could be another, 1 or 2 feet from there to maybe like a meter. But if we continue to warm it, then there's 200 years after 2100, there will be much more melting going on and much more thinning of the ice. And then we might get, several more feet of sea level rise just from Antarctica alone. I mean, we still haven't figured out all the details. There's a lot of uncertainties to do, and we're not exactly sure how maybe other parts of Antarctica are helping. So there's a lot of research going on, and people studying a lot of this glacier here. It's Thwaites Glacier at the moment, because all the models show that's where the most of the melting will happening in the near future, meaning the next 100, 200 years. So that's basically all I wanted to show. For that, I want to make a little plug for some colleagues and out of our larger project, University of Exeter in the UK and in Britain. They developed a game that kind of helps you to understand how the different ice sheet works. So basically you can, on the left side, you have a slider, you can increase the snowfall and make the ice sheet bigger or smaller, depending on the accumulation, the snowfall. And on the right, you can basically increase the temperature of the water, makes the water warmer and decrease melting. And I think the game, I'm not really good at this, but the game basically is you get a bunch of penguins, they run down here. And sometimes you have to see if they can meet the albatross here. So you have to bring the ice sheet on the same elevation level. And then, of course, the penguin has to try to, it will jump whenever the ice is open. So you have to get the opening, not like here in the middle, but basically where the fish is, so it can get to food. But you have to avoid the penguin to basically fall down where the leopard seal is lurking, and then the penguin will be eaten by the leopard seal. So it's a fun game, and if people are interested, that can try it out. It's freely available, runs on the browser or different things. And with this, I like to finish, and then hopefully we can have a lot of questions.
Great. Thanks, Frank. So what we'll do is I might have Rosalba, I'll have Rosalba share her the NASA GIS resources first. Frank, there are 2 open questions in the Q&A box if you do want to tackle those, and you can type the answers to those, or you can answer them directly live after Rosalba is done. Thank you. Rosalba, go ahead.
Thank you, Cassie. Hello, everyone. My name is Rosalba, and I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies. And I am very happy to be here to share some supplemental resources. I am sending some links on the chat, and I am going to share my screen now. Can you see my screen? Okay. So today I would like to highlight the Global Ice Viewer, the Scientific Visualization Studio, and a very cool interactive app that is called Ice on the Earth. So first, the Global Ice Viewer is an interactive that lets you learn about climate change, how it has affected glaciers, sea ice, and continental ice sheets worldwide. I just want to go very quickly to it. And with this interactive, you can see information and visuals about glaciers and Greenland and Iceland and the Arctic and the Antarctica. I'm focused on the Antarctica because of the topic today. So you can take a look at a map of major ice shelves in Antarctica. There is also an ice flow map, and you can learn about the speed of ice flow. You can also take a look at sea ice trends in the Antarctic Sea. And there are also visualizations of major ice disintegration. So for example, there's this one at Larsen B that shows the most pronounced ice shelf retreat. Pretty powerful visual. Let me go back to my presentation. The next resource is the Scientific Visualization Studio. So this studio works closely with scientists in the creation of visualizations, animations, and images so that we can better understand the Earth and space science activities that are happening at NASA and other institutions. And so the specific link that I sent on the chat lets you see a visualization with data from NASA's and the German Aerospace Center's twin satellites, GRACE and GRACE Follow-On. GRACE stands for Gravity, Recovery, and Climate Experiment. And so with this visual, you can see how Antarctica has shed about 150 gigatons of ice per year since 2002, which has caused a sea level rise of 0.4 millimeters. So yeah, this studio, again, like has tons and tons of videos and visualizations that you can download for free. So that was just an example, but definitely something that you want to check out. Next, there is an app called Ice on the Earth. You can download it also for free. And so it will let you monitor our planet's vital signs, such as sea level height and the Antarctic ozone. You can also trace the movement of water around the globe using a gravity map from the satellite that I was telling you before, GRACE. Well, it's actually twin satellites, GRACE and GRACE Follow-On. And then you can also explore many other satellites, including ISAT-2, that stands for Ice, Cloud, and Land Elevation Satellite. And so this satellite uses lasers and a very, very precise detection instrument to measure the elevation of Earth's surface. So with this, scientists can calculate the height of glaciers and sea ice and the changing ice sheets, including the ice sheets in Antarctica. So a very cool app to explore. And just a bonus resource, I did want to encourage you to visit NASA's Global Climate Change website. It has many quizzes and more interactives, the ones that I showed you and more. And so this specific one that I'm highlighting here is a 10-question quiz about the frozen poles to test your knowledge about the frozen poles and to learn more. And that's it. That's what I have today. Thank you.
Great, thanks, Rosalba. Okay, so Frank, we have some questions here. We are a little low on time, so let's try to take some of those. So starting with the first one, Neil was wondering if the pH of, I think this was probably more specific to one of the slides, if the pH was being used as a measurement for the water.
Yeah. So I only mentioned like with the CDD that we mentioned like salinity and temperature, but actually that we measure, the systems measure pH and oxygen and chlorophyll content and light submission. So there's a whole range of instruments that are going there. So I do this, and often also we're taking some water samples, and then sometimes I do an analytical pH calibration with the water samples as well. So I went into this because it's not so important for ice, but there's a lot of sampling. And while the ship goes, it actually measures pH from surface water all the time. So it's monitoring the part of the global monitoring of the pH on the ocean. So it's definitely happening.
Great.
All right, I can just go through the list here.
Yeah.
Can we measure the temperature profiles of bedrock? Well, bedrock is difficult. We can, and some people do actually measure sediments. So if you drill a hole and have temperature probes and a stick in the rock or in the sediment, you can get temperature profiles. So they do this. There's like probes you can lower from the ship to get temperature in the sediments, but you can't really drill in rocks easily from the ship and get temperature profiles. But you have to have a drill ship for that. So they do it, but they do it on land sometimes. So that's happening. And it's also a little bit like how much like warming happens from underneath the ice shelf and contributing to melting. That's studied as well. Antarctic and Greenland ice sheet melting at the same rate? Somebody asking. Well, at the moment, there's some glaciers in Greenland that are melting faster than the glaciers in Antarctica. Also, this seems to be changing with trains in Pine Island. I think because Antarctica is much bigger. So you see in the beginning, the component, it's from Greenland and Antarctica is at the moment maybe roughly the same. But we expect that Antarctica is going to overtake Greenland soon, since once the melt rates are increasing in Antarctica, and it's just much more ice there. But so some of the Greenland glaciers are faster in melting, but there's at the moment there's less ice and total. Can animals? There was a question by Yanis. Can animals sense when ice sheets are about to break off? I don't know that. I haven't been there, so it's a good question.
Curious.
So there might be some cracking and some noise, and I would imagine that it would be kind of transmitting through the water as well. So they might probably hear something. So there's other colleagues in Lamont actually studying what they call like ice quakes, when there's a crack of the noise that's made. It's almost like a mini earthquake when that ice is breaking off.
Yeah.
But some of it's big in Antarctica. You get more of these big chunks of ice shelf breaking off, so they're more like drifting away from the wind, and it's not so dramatic. Also, it's like really big icebergs.
Yeah.
Is the data collected from Operation Icebridge incorporated in these resources? So Operation Icebridge was actually, when I showed my slide with the satellites and the airplane, there was a gap between two satellite missions to measure the ice thickness, and they used an airplane to measure the height because NASA wants this continuous record. And so the data are incorporated in this study, like how much ice is lost, or like how the thickness changes over time, I think. Yeah, so definitely. And so that would be more a question, I guess, for another point if they included, but I would guess that they are. But I think operational outputs data, they're also all freely available.
Great. All right. Well, thank you, Frank. And we're actually just about out of time here. Any sort of last words? We'll share the link to the game as well as all of the resources that Rosalba shared as well. And yeah, Frank, any additional comments here?
No, I mean, it's really, I mean, the whole, I mean, I still enjoy going there. It's really fascinating to see this live in the ice. It's really exciting. And I mean, we've learned a lot about how the ice sheet works, but in the last like 10, 20 years, there was a lot of research done. But I think there's a whole lot we don't know, a lot of the details, and each expedition we learn new things. And I'm pretty sure that, you know, people who go and study ice sheets in 10, 20 years, like maybe a lot of younger people like listening in so many. So it's a lot of, it's still like a field that's growing, and there's a lot of work that needs to be done so we understand really what's happening. I mean, we don't know how much we have committed already in terms of sea level rise. And the big question is not like, are the ice sheets melting? Yeah, we know they are melting. The question is like, how much are they going to melt and how fast they're going to melt? It's makes a difference if you have like 2 feet of sea level rise in 100 years, or we have it in 150 years and things like that.
Right. Yeah, I think that's a really good point to end on. Last week we had Vicky Farini on, and she also talked about, you know, yes, we've come a long way in terms of research, and her focus was on technology and oceans research and things that we have already mapped, but that there's still so much left to know. And I think that's a really great reminder. And now we grapple with questions of predictions and projections.
Yeah.
And those are very tough questions to answer.
I mean, it's hard to see. So in Antarctica, we study this one glacier. We're studying it right now very intensively, but a lot of Eastern Antarctica, I mean, we don't even know like how deep the seafloor is in front of the ice. I mean, there's like, most of it is not really explored. And a lot of things will be changing now with more robotic technology, I guess, in the next 10 years, but we still probably have to get people there with ships as well.
Yeah, definitely. All right. Well, Frank, thank you so much for your time and for sharing this. And
Thank you.
I said, yeah, we'll share the recordings as well as shared. Thanks. Great rest of your day. Oh, I'm sorry. It looks like my internet was a little bit unstable there. So apologize if I just froze. So thank you again, everyone, for tuning in, and we hope you have a great rest of your day. All right. Thanks,
Thank
Frank.
you. Bye.
Bye.